Hey guys, Shay here with the second part of 6.2, and I am not going to sugarcoat it. This is going to be tough. Definitely tougher than the first part of 6.2, and arguably one of the harder things we'll do all year. With that being said, you will have the entire week to do this assignment, and we will probably be practicing it again to start next week. And as always, I can't encourage you strong enough to, try the problems. If you're getting stuck, reach out. I don't know how much you guys talk to each other right now, but I've done that for a lot of you where I've made a video when you've reached out, and it seems to have been pretty effective. So please continue to do that. Okay, at this point, we are going to be simplifying higher index radicals. And it's not bad when I say, like, this is what you've been doing so far. So far, you've taken something like, what is the cube root of 8? Which meant what number times itself 3 times equals 8, and the answer was 2. So we've seen that. Today, we're going to get at things like, what is the cube root of 28? What number, when multiplied by itself 3 times, equals 28? And the answer is, there's not really one. There's not a integer, or the type of number we're used to. So now we're going to end up having to find a way to simplify this. Maybe this is a bad one. Let me just pick a quick example. Say I want to do the square root of 50. So what number times itself equals 50? Well, no number times itself equals 50. However, 50 can be broken down to 25 times 2. And the square root of 25 is 5. So this turns out to be the same thing as 5 root 2. So evaluating the square root of 50 means to turn it into 5 square root of 2. And that's what we're going to be learning to do today. So you don't quite have that lesson yet. I'm going to teach it to you. But it's definitely trickier than this. Here there is a number that when we multiply by itself 3 times equals 8. That number is 2. Technically, there is a number when I multiply it by itself twice equals the square root of 50, but that number happens to be an irrational number, not the kind of thing we're used to. So to get into this, I would suggest pausing and writing this core concept down here if you didn't print out the guided notes. I'm going to go through it, and I might come back up to this example to explain what's going on. So we're going to let a and b be real numbers and n be an integer that's greater than 1. So our indexes have always been just positive whole numbers. So the n value is the index. It's going to be a positive whole number. And we don't take the first root of anything because that doesn't change anything. So they generally start at the square root and then move up. What this is telling me is if I'm taking the nth root of some two numbers being multiplied together, it's the same thing as the nth root of the first times the nth root of the second. To see how that works, that is exactly what I did up here. I didn't show it that way yet because I hadn't explained it to you. I'm going to switch pens so we can see this. So the square root of 50 doesn't look like a multiplication problem, but I could think of that as the square root of 25 times 2. That is another way of writing 50, isn't it? It's 25 times 2. So this rule tells me that if I have the nth root, in this case a square root, the nth root of a product, it's equal to the nth root of the first times the nth root of the second. So the square root of 25, we can evaluate what number times itself equals 25. Well, that is the number 5. 5 times 5 is 25. The square root of 2 is just the square root of 2. There is no integer that when multiplied by itself would equal 2. It's an irrational number. So in essence, that is what we are doing today. I'm kind of actually really happy with the way that displayed. I hope that makes a lot of sense to you. When you have a number inside the radical called the radicand that doesn't evenly factor out the way that these ones do, you have to turn it into two numbers that multiply into it or more. And we'll see that as we go. And then you can evaluate the nth root of each part. And again, this is the square root. Some people were confused by that whole thing, the nth. The nth just means I can make the n a square, I can make the n a cube, I can make the n the 5th power, the 6th power, the 7th power, the 128th power. The nth root just refers to which number goes in the index. How many times are we looking to multiply a number by itself? Okay, And quite frankly, if it can be done for multiplication, it can be done for division, because mathematically multiplication and division are really the same concept. So if I'm taking the nth root of a fraction, it's the same as the nth root of the numerator divided by the nth root of the denominator, or to make that a little simpler, the nth root of the top divided by the nth root of the bottom. Okay, so that is in theory, that is the entire lesson. However, it's pretty hard to do, and it's going to take some degree of knowing your multiplication table. And if you don't know your multiplication table, you're going to have to keep trying to divide by numbers till you find something that works, and that can be very, very frustrating. This is one of these situations where, high school teachers get mad when elementary school and middle school teachers are like, just use a calculator, because things kind of fall apart here. You can try, but your calculator is not going to do the cube root of 54 unless you have about $150 calculator. I mean, they exist. I have 2 of them. But chances are you guys don't have them, and we are going to need to find things like this, which we call exact answers, instead of decimal point approximations, which is what most of your calculators would give you. Okay, let's do some practice. Definitely you guys want to take notes on this. You can pause it as much as possible. I'm going to try to explain these sometimes multiple ways, sometimes only one way, because they really only present that way. All right, let's see if we can use these rules to evaluate the cube root of 54. So first thing is, if it was perfect, we'd want to do that. A perfect would be like the cube root of 8 is perfectly 2. So is there a number multiplied by itself 3 times that equals 54? I think we can do a pretty quick check on this. We know 3 times 3 times 3 is 27. And then let's try the next number, 4. 4 times 4 is 16 times 4 is 64. So no, there is not something that's going to be perfect here. We know that the actual value of the answer is some number that falls in between 3 and 4. Now to figure out what it is. Well, this suggests if I can't find it perfectly, I should try to break that number, the 54, apart into 2 things that multiply to 54. Off the top of my head, well, actually, I shouldn't even say off the top of my head. This is the strategy that we usually use. If it can be divisible by 2, that's a nice, easy starting point. You usually recognize it. All even numbers can be divisible by 2. So let's take this, and I'm going to divide it by 2. That means I have the cube root of 2 times 27. Now, I'm already pretty happy here because off the top of my head, I know that 27 is a perfect cube. But let's rewrite this using this definition. I now have the cube root of a product. I'm going to write it as the cube root of the first term times the cube root of the second term. This is the cube root of 2 times the cube root of 27. And now we see if we can simplify any of these. The cube root of 2, definitely not. There's no number we can think of. There's no rational number that when multiplied by itself 3 times would equal 2. Matter of fact, the name for that number is the cube root of 2. We can't simplify it any more than that. However, what number multiplied by itself 3 times would equal 27? That's 3. 3 times 3 is 9, times 3 is 27. So this number, when I simplify, the cube root of 27 is 3. Please do not write it's the cube root of 3. That wouldn't make any sense whatsoever. The cube root of 27 is 3. Again, the translation here. What number, when I multiply by itself 3 times, would equal 27? The answer is 3. So I have 3, and then I have this thing left. Usually in math, we write these after. So it's 3 times the cube root of 2. And that's our answer, 3 times the cube root of 2. Now, if you didn't recognize that 27 was a perfect cube, you would divide it. So I'm going to show this off to the side. You just keep going. You get 27, well, that's 3 times 9. And 9 is 3 times 3. So note, 27 is actually 3 times 3 times 3, and you have 3 cubed. You'll see that more as we go. Again, I can't stress enough, the better you know your multiplication table, the easier this type of work becomes. All right, the 5th root of 224. Is there a number that when multiplied by itself 5 times equals 224? Spoiler alert, there is not. So, I'm going to show this problem 2 ways. The first way is, hey, I'm a math teacher and I do this for a living. So don't get upset if you wouldn't think about it this way. I'm going to show it the way that's kind of more natural to people as they're learning it in a second. So if I look at this, ideally, and again, this comes with a lot of practice, and I apologize that you guys are staring at that cut on my hand. Sorry, I should have put a Band-Aid on. If I had to do this in an ideal way, I would want to break 224 into something that I knew was a perfect fifth root, or a perfect something raised to the fifth power. I happen to know that 32 is 2 to the fifth power off the top of my head. So, knowing that, I did what's 224 divided by 32. Luckily, it went in even. 32 times 7 is 224. Well, that's nice because that means I can just say this is the fifth root of 32 times the fifth root of 7 by the rule we learned. All right, awesome. The fifth root of 32, I already said, is 2. The fifth root of 7, we can't think of a number that I can multiply by itself 5 times that equals 7. It is, in fact, an irrational number. And this is our final answer. The fifth root of 224 is exactly the same as 2 times the fifth root of 7. So this is simplified. It's kind of hard to argue that. All right, how this is probably going to look for most of you guys. All right, I don't know what goes into 224 off the top of my head, so I'm just going to divide it by 2. Well, that's 2 times 112. Now note, technically all of these should be under fifth roots, but for the sake of saving space, I'm not going to show that. All right, well that 112 can also be divided by 2. That's 2 times 56. All right, well 56 is 2 times 28, which is 2 times 7. All right, let's see. Oh, sorry, that's 4 times 7. And 4 is 2 times 2. I could have done 2 times 14 there. Instead, I didn't. So when we get to the end of these pyramids, note I have 224 is 2 times 2 times 2 times 2 times 2. It is 2 to the fifth power times, let's see, are we at the end, I still have that 7. Oops, that's just a 7. So note, 224, if I broke it down the long way, still turns out to be 2 to the fifth times 7. And all of that I want to be taking the fifth root of. So that can be thought of as the fifth root of 2 to the fifth. Note, radicals and exponents are the inverses of each other. So that's just going to equal 2. And I still have times the fifth root of 7. So note, I get the same answer. It was a little bit longer to get there. There's no question that the more you know your multiplication table, the easier it is to pick out some of these. And I don't want to make it be like I don't know, 9 to the fifth off the top of my head. That's a huge number. But your 2s and 3s to powers you start to get to know, and if you can recognize they go into things, it does cut down on the work. This was a lot shorter than that. That being said, this is only a shortcut if you happen to recognize something like this. Otherwise, if you go searching for them, it may take forever, and you'd be better off just breaking it down any numbers you can think of at a time. If 2 goes into it, divide by 2. If 3 goes into it, divide by 3. Just keep trying to get to smaller and smaller numbers. Technically, any number can break down into solely the product of primes. 2 is a prime number. 2 times 2 times 2 times 2 times 2, that's all primes. 7 is a prime number. So I can take any composite number and multiply it and break it down so it is just the product of primes. That's actually a really special mathematical theorem called the prime number theorem. So that can be done. I didn't do it here. I didn't go to the prime factorization, but I did when I broke down 27 the other way. Note, it was 54 was 3 times 3 times 3 times 2. So 3 is a prime number, 3 is a prime number, 3 is a prime number, 2 is a prime number. You can always just keep splitting until you have prime numbers. It's not the most efficient way, but it works. And as you're starting to build up this skill, that might be the way to do it. Okay, I'm going to keep going here. I know this is going to take a while. So note, here I have 5 times the fourth root of 243. just like when we have a letter written next to a number, it's implied there's multiplication there if there's not a sign. So 5 times the fourth root of 243 means I need to break down the fourth root of 243. Again, off the top of my head, I look at this, it's not even, right? So I can't divide by 2. I'm just going to try. What can I divide by? Well, I can divide by 3. If I divide by 3, it happens to be 81 times 3 is 243. Well, that's pretty nice because luckily I recognize that the fourth root of 81 is 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. Again, you could break it down to 9 times 9. If you do 9 times 9, that's 3 times 3 times 3 times 3. Hence, you still get the fourth root of 81 is 3. So here it becomes 5 times the fourth root of 81 times the fourth root of 3 by the rule we started off this lesson with. The fourth root of 81, as we said, is 3. So we get 5 times 3 times the fourth root of 3, which is 15 for root 3. And that's that. That's all there is to that one. Again, you could have made it longer if you didn't recognize 81 was a fourth power. You would have kept going. 81 is 9 times 9, which is 3 times 3 times 3 times 3. And you see that you end up still with 3 to the fourth power equaling 81. All right, moving on again. Negatives. With negatives, we got to make sure this exponent, the index is odd. If the index is not odd, this wouldn't make any sense whatsoever. No number of times itself, an even number of times, could ever be negative. However, that's not the case here. Note, I see a fifth root. I'm going to think 32 again. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So I happen to guess right. Negative 32 times 3 is 96. Meaning, the fifth root of negative 96 is the same as the fifth root of negative 32 times 3, which we know from our rule is the same as the fifth root of negative 32 times the fifth root of 3. What number when multiplied by itself 5 times is negative 32? We just went over that. It's negative 2. This cannot be simplified anymore. Fifth root 3. There's our final answer. Moving on. Again, I know that it's really weird teaching this without a back and forth, without you guys being able to ask questions as we go. So send me the questions. Send them to me via email. 81 to the 3/4. So now we got to combine some of the stuff we've learned over the last few lessons. If I want to do 81 to the 3/4, I first got to remember that that's the same thing as the fourth root of 81 raised to the third power. So we're using our exponent to radical notation. That tells me that I can now go down here to 81 and try to figure that out. Now, I know that this is going to be 3. It kind of jumps out at me. But in case you didn't, again, that's the fourth root of 9 times 9, because that's 81. Well, 9 times 9 is 3 times 3 times 3 times 3. So we end up with the fourth root of 3 times 3 times 3 times 3, better known as the fourth root of 3 to the fourth. And all of that still being raised to the third power. Well, what is the fourth root of 3 to the fourth? This literally means what number, when multiplied by itself 4 times, equals 3 multiplied by itself 4 times? Pretty clear answer there, 3. Our exponent, we didn't deal with that yet. We just turned the fourth root of 3 to the fourth is 3. Now we have that cubed. And our final answer is 27. 3 times 3 is 9, times 3 is 27. Okay, fun stuff. Number 6. Again, order of operations never disappears in math. We do not want to do multiplication before exponents. In PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, those need to be bundled. All right, do what's in parentheses. I can't do anything to negative 27. That's gone. Move on to exponents. So I've got to take care of the exponent before I take care of the multiplication. Changing this to radical form, this is going to become the index. So we have 2 times the cube root of negative 27. And then we know that the exponent 2 can either go on the inside or the outside. Our math will be a lot easier if we put it on the outside. So still, let's follow our order of operations here. Can we simplify the inside of these parentheses, the cube root of negative 27? Sure, the number that multiplies by itself 3 times to equal negative 27 is negative 3. Our problem now looks like that. We can't do what's in parentheses, so now we got to choose between exponents and multiplication. PEMDAS says take care of the exponent first. Negative 3 to the second power is positive 9. Negative 3 times negative 3 is positive 9. 2 times 9 is 18. Well, this is definitely an example of it's like finally, oh my God, this did make it a lot simpler. Looking at 2 times negative 27 to the 2/3 power, that's pretty confusing. The number 18 is very straightforward. All of these are technically considered simplified when we finished them. I just think this is the one that finally got us back to the type of number we're used to, back to an integer. That is not to put down irrational numbers. Irrational numbers are extremely, extremely important in the fields of math and science. Okay. 20 minutes in, we're not done yet. Shouldn't have used a black pen on the other side of this page. Here, I'll rewrite over here so you can see what's going on. This is 25 to the negative 3/2 power. Oh man, we are just putting all of the rules together. So let's see if we can rewrite this in a radical form. Our index is going to be 2, the denominator of the fraction. So we have 2 times the square root, really, the 2th or square root of 25. And then all of that will still be to the negative 3rd power. Square root of 25. What number, when multiplied by itself twice, equals 25? The answer is 5. So this problem becomes 5 to the negative 3rd power. But as we learned a couple lessons ago, negative exponents not considered simplified mathematics. So this actually becomes 1 over 5 to the 3rd power, where the exponent becomes positive on the bottom of the fraction. And then we simplify that. 5 to the 3rd power is 5 times 5 is 25 times 5 is 125. All right, so that's that. That one was not bad. This next problem is a train wreck. I don't even, I'm debating right now, even though I've already planned on doing this, whether we should do it. Let's save it for another time. If you're curious, if you want to try this on your own, the answer from what you guys have seen so far would be 1 over 2,304 times the cube root of 6. So if you want to try that and let me know if you're getting it or not, and ask why, that's fine. If not, I'm okay with you ignoring this. The reason this is also such a train wreck is there's a rule in mathematics we haven't learned yet that says you can't leave these radicals in the denominator of fractions. So technically, this is going to become the cube root of 6 squared, or the cube root of 36 over 2,304 times whatever 6 squared is. Nope, sorry, just times 6. Times 6. And I'm not doing all of that out right now because you guys, you're not there yet. But I'm not going to throw another teacher under the bus. But another teacher chose this problem when I was solving, and I just was like, why? Why now? We're not there yet. Okay, sorry for that detraction there. Okay, again, my marker bled through from the other page. So example 1 here, or part 1 of example 7, should say the 4th root of 81 a to the 4th. All right, cool. So we've just been going over how to break down these things with numbers in them, and now we're going to have letters thrown in as well. Good news is this first one is simple, at least. It will get worse. We know I can break the products apart, and this is the same thing as the 4th root of 81 times the 4th root of a to the 4th. The 4th root of 81 we have already seen numerous times today is 3. The 4th root of a to the 4th. What number, when multiplied by itself 4 times, equals a multiplied by itself 4 times? Well, that is just a. Again, I speak it out like that because that's the logical way of thinking about it. The other way of thinking about it is exponents and radicals are inverse processes. They undo each other. So if I raise something to the 4th power and then take the 4th root of it, they effectively cancel each other out, and we're just left with the original number. So there you go. 3 times a. We never leave written that way. We really just write 3a. Okay, again, another one that's not too terrible yet. The cube root of 125x to the 5th. Well, we know that's the same thing as the cube root of 125 times the cube root of x to the 5th. This is going to become the hard part, or more interesting part that we have to focus on, and I will explain it in 2 different ways. Cube root of 125, we can break down. You could break this down as 25 times 5, and then 25 is 5 times 5. I happen to know off the top of my head the cube root of 125 is 5. All right, so we can just go straight to that. Here is an interesting part. Now, it uses our rules of exponents. So I'm going to break this apart. I'm just going to write it in here. X to the 5th is the same thing as x cubed times x squared. Do you remember from our lesson on multiplying common bases, we add the exponents, right? So x cubed times x squared, I'd add the exponents, and that's actually equal to x to the 5th. So again, I'm actually just taking the inside of the radical and I'm breaking it into factors, things that multiply together to it. And we can apply our rule yet again. That means 3 times the cube root of the first part times the cube root of the second part. Well, the cube root of x cubed is x. Again, we talked about this. What number, when multiplied by itself 3 times, equals x multiplied by itself 3 times? X. This, on the other hand, cannot be simplified at all. It is just the cube root of x squared. And I'll show you another way of thinking about that. Okay. The other way I think about these, if I wanted to simplify the cube root of x to the 5th, is we really divide the power on the inside by the radical on the outside. So how many times does 3 go into 5? It goes in once. All right, so I'm going to pull 1x out because it went in once. And then what's trapped on the inside is the remainder. Well, 3 goes into 5 once with a remainder of 2. That's how I figured out the exponent on the inside. I'm going to show that a similar thing off to the side now in case you want to use that rule. It works. It's the same thing as doing this. It's a byproduct of doing that, but a little bit quicker. So let's just say I had something like the square root of m to the 9th. All right. I could break this down as m squared times m squared times m squared times m squared times m. That would be m to the 9th. Or I could say, well, 2 goes into 9 how many times? 2 goes into 9 4 times evenly. So that's m to the 4th on the outside. What is left over? 1m. All right, so again, this is a shortcut method for breaking down the radicand into factors that multiply to it. Maybe we can utilize that on the last 2 problems. Long video here. I apologize, but I'm sure you guys can see that I needed to give you guys a lot of examples because this is not a particularly easy topic. All right, so we're going to break this down as the 4th root. I'm going to try it the shortcut way first, and then I can explain it the other way. The 4th root of 625, and let's just say times the 4th root of x to the 4th times the 4th root of y to the 7th times the 4th root of z to the 8th. I'm going to try to use my shortcut rule here so you can see how effective it is. The 4th root of 625, well, 5 times 5 is 25, times 5 is 125, times 5 is 625. So that's 5. X to the 4th root of x to the 4th, we already know those are going to cancel out. That's going to just become x, so we have 5 times x. Here, let's use our division rule. How many times does 4 go into 7? It goes in once with 3 left over. I like that. I mean, that's a lot easier. How many times does 4 go into 8? It goes in twice, so we have the exponent of 2 with 0 left over, so I don't have to write anything there. And when we structure these, we always put the radicals at the end. So this becomes 5 times x times y times z squared times the 4th root of y cubed. It's another one of these that doesn't look very simple, but that is the simplified version of it. And yeah, so I like that shortcut. If you didn't do that shortcut, you would rewrite, let's take this term here, the fourth root of y to the seventh, you would probably think of as y to the fourth times y to the third. Note, multiplying common bases, we add exponents, so y to the fourth times y to the third is the same as y to the seventh. And then when I split it apart, we end up with the fourth root of y to the fourth, which is y times the fourth root of y cubed, which is exactly what we got using my shortcut method. All right. Oh man, we're at 30 minutes. Last one, finally. When we were in class, I get to not talk the entire time. This is a lot harder for me. All right, so let's break this apart to the cube root of 16. Let's see, times the cube root of a to the fourth, times the cube root of b to the fourth, times the cube root of c to the seventh. All right, 16. 2 times 2 is 4, times 2 is 8. So let's break this apart. This is 8 times 2 is 16. So it's the cube root of 8 times 2. The cube root of 8 times the cube root of 2. Cube root of 8 is 2. Oh man, a lot of work to get there, but we finally got to 2 times the cube root of 2. On the letters here, the variables, I am just going to use my shortcut rule. How many times does 3 go into 4? It goes in once, so this is going to become a times the cube root of 1a is left inside. 3 goes into 4 once with 1 left over. How many times does 3 go into 4? The exact same thing for b. It goes in once with 1 left over. How many times does 3 go into 7? It goes in twice, so this is going to be c squared. That's where the 2 goes. It goes in twice. We make that the exponent. And what is left? Well, let's see. If it went in twice, that was 6. So that's a remainder of 1. 1c is left on the inside. So writing these all together, I now have times a times the cube root of a, times b times the cube root of b, times c squared times the cube root of c. How we finish these is we take all of the terms that are in the cube roots and we just put them back together, and all of the terms that aren't. So let me see if I can show this. I'm going to switch colors here. So things that are not in the radical, 2ab c squared. So I start off with 2ab c squared. Those are all outside of the radical. And then I'm going to take all of the things that are left in the cube root, 2a, b, c, and leave them in there. All right, guys, I know that was a lot. Be patient with this stuff. Do a little bit at a time. Don't anticipate finishing this assignment in one sitting. It's probably going to be more like do a problem or two, send Mr. Shea an email asking a question because you're stuck, and I'll get back to you. Once you see that, maybe try another couple until you get stuck again. I hope everyone's doing well. I'm sorry that you have such a difficult lesson to do in this remote format. Take care, guys. Bye.